This is our formal Lab 1. We designed an experiment that looks at how a change in height affects the energy of a ball when it's bouncing on a surface. Our test question is, how does a change in initial height affect the energy of the system right before the first and second bounces of the ball? Our results showed that an increase in initial height leads to an increase in both kinetic and total energy of the ball right before each bounce. Our independent variable in this experiment is the initial height of the ball, and our dependent variable is the energy of the system. We are holding mass, camera angle, elasticity, and initial velocity constant, and we're looking at both the kinetic and potential energy equations. Our method, we are dropping a ball from different initial heights and then tracking the position and velocity of the ball to calculate the energy of the system right before the bounces. We hypothesize that if we drop a ball from a higher initial height, then there will be an overall larger energy of the system. A potential flaw we have is we assumed air resistance is negligible, which if included would be shown through a loss in energy before any bounce happened.
For our system schema, you can see our ball interacting with the ground with the force of gravity pulling it down. And here is a screenshot of our tracker window. So for our tracker data, we put in the data of each of the 4 different heights. This is our 3-inch, 6-inch, 9-inch, 12-inch. And you can see in each of them, there are some consistencies for the y component of position and velocity. It's very much as expected with the parabola or half parabola for position. And then with velocity, you can see it's almost a constant line with a negative slope. And then for acceleration, however, it's a little bit more varied. We wanted to see a line with a constant slope, but it's a little bit more varied than that. And then here's our table of data. We put in the drop height, bounce height, velocity before each bounce, and instantaneous kinetic energy before each bounce.
Here we have a model of the motion of the ball. You can see at the top here, the total energy is all potential, and right as the bottom, it is all kinetic. So these are directly related to one another, where at the furthest bottom point, the total energy should be equivalent to the very top or the original drop height of the ball. You can see here that as the ball bounces up, it has less height. This is because we have a decrease in energy lost to internal energy when the bounce occurs. So the mathematical reasoning for this is we were able to show that there would be a change in potential energy because of the change in height. Because we know that potential energy is equivalent to the height times gravity times mass, and considering mass and the force of gravity are kept constant, we know that we will have a higher potential energy as height increases, which is directly proportional to the kinetic energy as potential energy is converted to kinetic energy during the fall. Again, here are our motion maps. You can see at the beginning of each, there's relatively the same motion, but as they get further into the bounce, the 12-inch has more energy and higher kinetic energy that's visible because it is accelerating more. And here's our pie graphs. Again, similar proportions of the types of energy, but the total energy is what's increasing, as 3 inches is the smallest, and then 12 inches being the largest total energy in the system.
Okay, so identifying and minimizing error. So our possible sources of error were camera angle, unintended force, video frames, and tracker error. And we attempted to minimize each of these varying sources of error through a variety of different methods. Okay. Quantitative error, we determined our average error from adding together all of the errors for each of the 4 drops, and then just determining the average of that, and we determined our total percent error as 1.13. Quantitative conclusions, the total energy of the system right before the first bounce, we found increased linearly by an average of 54.2, as the initial height of the ball increased by 3 inches for each drop. And the total energy of the system right before the second bounce increased linearly by an average of 35.47 as the height increased by 3 inches. Qualitative conclusions, a greater initial height of the ball resulted in a greater kinetic energy of the system before the first bounce and second bounce respectively. And since the total energy of the system before each bounce equals the kinetic energy of the system at those points, we can conclude that a greater initial height is conducive to a greater total energy of the system. Thank you.